Hello everyone and welcome to this machine learning playlist. Today we are covering an important topic, so whether you're someone who is absolute beginner or you have some experience with machine learning, this playlist has been designed in such a way that it will be easy to follow for everyone. Also packed with lots of values and information, and it will be really helpful for you, especially if you're preparing for a machine learning based job role like data analyst or data scientist. So please subscribe to the channel and drop a like below to support our work, and without any further delay, let's get started with today's topic. Hello and welcome to this new lecture where we are going to understand the methods of evaluating a classification model. So far within this playlist, we have understood that how do we solve a classification problem using a machine learning technique. But after training a machine learning model, it is also important that we try to evaluate the performance of the model to understand how reliable the model is. So within this lecture, we are going to cover some important topics like confusion matrix, accuracy, precision, recall, and F-beta score. Pretty much everything that you need to understand and you need to be aware of at this point of time, and also really important from the interview perspective as well. So without any delay, let's get started. Let's start by understanding a confusion matrix first. Suppose that you are trying to solve a classification problem where you are trying to classify between two categories like yes and no, or let's say 1 or 0. Okay. In this case, where you have only two categories, a confusion matrix will be a 2 by 2 matrix with 2 rows and 2 columns. So let's understand the structure of this matrix. On the horizontal axis, we have the predicted value. It could be true or false, or let's say yes or no. And on the y-axis, you have actual values that you are trying to predict, which will be yes or no, or true or false. For demonstration purpose, as a base, let's consider that we are trying to classify between two categories, which is spam or ham. So as an actual value, an email can be spam or not a spam, which is ham. So when the email is a spam email and you are also predicting it as a spam, then the prediction is considered as true positive. In contrast, when the email is not a spam or a ham and you are also predicting it to be a ham, then it is considered to be a true negative prediction. With a good machine learning model, we try to maximize these two numbers as much as possible. However, on the other hand, if the actual value is saying email is not a spam or a ham, but you are misclassifying it as a spam, which means you are making a mistake over here, then the prediction will be called as false positive because you are falsely calling the email as spam. In contrast, if the email is spam, but you are predicting it to be ham, that means you are incorrectly predicting it as a non-spam email. That will be called as false negative prediction. With a good machine learning model, we try to aim for a higher value for these two boxes, and we try to aim for a lower value for these two boxes where we are making mistakes. And this particular error is called type 1 error. In contrast, this error is called type 2 error. So let's focus more on this type 1 and type 2 error, and we'll try to understand these two in more details. So let's say that there is a new email which is actually not spam, which means the actual value is false, but you are incorrectly classifying that email as a spam email. In that case, due to this type 1 error, you might lose this email that could be related to a job offer, or maybe a medical report, or maybe a passport application status. In a nutshell, you might lose an email which is important for you. In contrast, let's say you received an email which is actually a spam. So the actual value is a spam, but this time you are miscorrectly predicting it as a ham email. Then you are facing an issue of type 2 error. For a spam ham prediction use case, type 2 error is not that sensitive because finding a spam email in your inbox is kind of usual thing and it is not causing you a huge loss. But within this use case, type 1 error could be dangerous for you. Similarly, there are different types of use cases within machine learning where type 2 error could be more dangerous. We will discuss these things in more details as we move further. So for the time being, I hope that your understanding around confusion matrix is pretty much clear. So I will quickly erase all of this. And since we have understood the concept of confusion matrix, let's move ahead and explore topics like accuracy, precision, and recall. So let's start with accuracy first. Accuracy is true positive plus true negative divided by total. So let's break this down further. Let's consider this target variable where you have following values with only two categories, either 1 or 0. And let's say your machine learning model is predicting following values. So it is classifying it as 1, then 0, then 0 again, then let's say 1, 1, then 0, and then 1. Now let's check that how many predictions among these are actually correct. So this is correct, this is correct, this one is correct, this is incorrect, this is again incorrect, this is incorrect, this is correct, and this one is correct as well. So true positive plus true negative will be all these correct values. So we have 1, 2, 3, 4, and 5. So on the numerator we have 5 divided by total, which means including the correctly classified data points and incorrectly classified data points. In other words, total number of records. So that is 8. And our accuracy over here will be somewhere around 0.62. So it means your model is performing with 62% accuracy. So accuracy is a matrix that you should be using when you have a balanced data set. In simple words, if you are trying to classify between two categories, let's say zeros and ones, then their count should be equal within the entire data set. Because in contrast, accuracy fails to evaluate the model really badly when you're working with an imbalanced data set. So I will give you an example to understand this in details. Let's consider a data set of 100 records, and this 100 records has 95 ham emails and only 5 spam emails, which means this data set is heavily imbalanced. And over here, let's say that I'm working with a super dumb machine learning algorithm, or instead I'm simply using a function which is not even a machine learning algorithm, and I have created the function in such a way that whatever data you will provide to this function, it is going to classify that as ham. Even it is a spam, it is going to classify that as ham. And now if I try to evaluate this dumb function with accuracy, it is going to have an accuracy of 95%, because by default my function is going to classify all the emails as ham. So if I am going to test it on 100 records, without any effort it is going to correctly classify 95 records and making mistake with only 5 data points. And even being a dumb algorithm, it is able to achieve 95% accuracy. And this is why, a part of accuracy, we need to have other options like precision and recall that we are going to understand one by one. So let me quickly first erase all this. So the formula of precision is equals to true positive divided by true positive plus false positive. Let's try to understand what this means. So when we are working with precision, we need to consider the predicted values as base. I'll try to explain what I mean. So among all these predictions that we have made earlier, considering 1 as spam and 0 as ham, we are trying to understand that out of all these spam predictions, like these data points, how many we have got right. So let's check them one by one. So these two are correct, this is incorrect, this is incorrect, and this one is correct. So working on the same formula, it is going to be true positive, which means where the actual value was spam and we also predicted it as spam. So that total count here is 3. So I will put it 3 divided by true positive, which is 3, plus false positive, which means these two data points, which was false positive. So it is going to be 2. This value will be the precision, that is going to be 60%. So most important thing that we need to understand here, that in which specific case we will be using precision. So we use precision with the use cases where the main focus is to reduce type 1 error. As we have discussed previously, in case of an email which is actually a ham email and we do not want the classifier to classify it as spam, otherwise we might use an important email. In such cases, instead of using accuracy or any other metric, we would go with precision. But not always your focus will be on reducing type 1 error. There will be few use cases where type 2 error will become more sensitive. So let's discuss a situation like that. Imagine a use case where you are trying to predict if a patient has cancer or not. So the values are going to be either yes, which means the patient has cancer, or no, he doesn't have cancer. Okay. In this particular use case, if the actual value is yes, which means this one that says patient has cancer, but you are predicting it as false, which means the patient does not have cancer. That will be a type 2 error. In contrast, if the patient does not have cancer, which means this one, actual value is false, and you are predicting that patient has cancer, this one. So that will be an issue of type 1 error. And as you can understand easily, over here in this specific case, type 2 error is more sensitive, because if there is a patient who does not have cancer, if he is healthy, and we are incorrectly telling him that he has got cancer, that is not really a critical issue, because after going through a couple of tests and diagnostics, eventually he will realize that he is out of risk. But in the other situation, let's say if the patient has cancer and he needs to undergo a treatment immediately, and your machine learning classifier is incorrectly classifying it as false alarm and saying he does not have cancer, then of course the patient will not go for any treatment and his condition will become more severe. So this is an excellent example where type 2 error becomes really critical. So let's understand that how do we tackle this issue, and we are going to tackle it by using recall. So we calculate recall using this simple formula that says true positive divided by true positive plus false negative. So previously in case of precision, we were considering the predicted truth as base and we were taking account of that. In contrast, in case of recall, we are going to consider the base as actual truth, because our focus is going to be around the actual patients who have got cancer. So let's see how do we calculate recall. So our true positive here is going to be this 1, 2 and 3. So I'm writing 3 divided by 3 plus false negative, the alarming thing that we are trying to avoid. So we have a false negative over here where the patient has got cancer, but it is misclassifying it, and I think that's the only one. So it will be 3 plus 1 is equals to 3 by 4, and the final output is going to be 0.75, which means the model has a recall value of 75%, which is really bad, because if you rely on this model, then you are putting 25 out of 100 patients on risk. And with such use case, even a recall value of 99% is not that good, because it denotes we are putting one patient out of 100 at risk. So we will try to achieve even higher recall value, like 99.999, something like that. So in a nutshell, we use accuracy when we have a balanced data set. So I will write it here, balanced data set. When we are working with precision, it considers the true predicted as base value in order to reduce the type 1 error, so that, for example, we do not lose any important email which has got classified as spam by the classifier. So when you are using precision, you will use predicted truth as base to reduce type 1 error. And when you are using recall, you generally use it to reduce type 2 error, and it considers base as actual truth. So I will write it here. It considers actual truth as base. So that was all about accuracy, precision and recall. So we have understood that we are going to use accuracy with a balanced data set. We will use precision where the focus is to reduce type 1 error, and we are going to use recall when the focus is to reduce type 2 error. But what if you are working with a use case where type 1 and type 2, both the errors are really sensitive, and you cannot afford to make mistakes with both of these errors? This is a situation where you need to have the understanding of F beta score. So let's move ahead and cover that topic now. So F beta score is a metric that you will use when the type 1 error and type 2 error both becomes important. This is a simple formula of the F beta score that says 1 plus beta square. By the way, you can adjust this value of beta and we will discuss how, multiplied by the product of precision and recall divided by the product of beta square and sum of precision and recall. And this F beta score is called F1 score when we choose the value of beta as 1, and similarly F beta score will become F1 or F0.5. I think I have made some mistake here. Actually this should be F2 or F0.5 when the value of beta is either 2 or 0.5. So if you are choosing the value of beta as 2, it becomes F2 score. If you are choosing the value of beta as 0.5, it becomes F0.5 score. But you might feel like there is too much confusion. How do we choose the optimum value of beta? Should it be 1, 2 or 0.5? So let me simplify this for you. For problems where type 1 error has more impact compared to type 2, we reduce the beta value to 0.5. Similarly, we keep the value of beta as 2 when type 2 error has higher impact. However, with the case where both has equal impact, we will go with the beta value of 1, and that will be called F1 score, which is typically used, becoming 2 multiplied by product of precision and recall divided by I need to remove this part because this is becoming 1. So divided by precision plus recall. That's it. So you will use this particular formula when both type of error has equal impact. F1 score is also called harmonic mean, which means it comes within this format. In case you are not aware with the concept or the properties of harmonic mean, then let me quickly simplify this for you. Let's say between X and Y, or let's say between precision and recall, or between type 1 or type 2 error. Harmonic mean works in such a way that if the value of type 1 error is lesser, then the entire equation or the entire F1 score will be biased towards that, and it will try to focus and improve that particular area. Similarly, if the type 2 error or the recall value is on the lesser side, then it will start declining towards that area to enhance the performance over there. And this is why, because it comes within a harmonic mean equation, we use F1 score with the use cases where we are providing equal weightage or equal importance to both type of errors. And with that being said, we have covered everything for today's lecture. So I hope that you found this video helpful. If yes, then please consider showing your support by dropping a like below. Consider subscribing as well if you are not yet subscribed. And I would suggest that you save this video to your YouTube playlist, because this is a topic that you might need later on. In fact, you will definitely need it later on, especially when you get an interview call. It will become important to revise these topics. So that was it for today's lecture. Thank you very much for watching till the end. You have a nice day ahead.